Well, hello folks, for Saturday the 4th of September, and we're in lockdown still, and we're likely to be there for another 3 weeks according to Dan Andrews and the Victorian government. We're going through yet another peak of, hopefully a peak of infection leaking over from New South Wales. What can one say? Well, the first thing I have to do tonight is to acknowledge a very nice gift from an old friend, John Fleming, who has sent me a whole pile of these. These are the magazines of the Historical Radio Society of Australia. Very nicely produced, and I can thoroughly recommend becoming a member of the society. There's an article on radio sondes. There's one being launched from Macquarie Island in the Australian Antarctic Territory. I've must admit to have been probably unjustly putting down the Historical Radio Society for some years. I was their secretary 35 years ago in 1986, only a few years after their foundation. And my interest has always been in the software of radio, recordings of radio programs, rather than the hardware, the radio themselves. In any case, I just don't have the space here or elsewhere in my property to store a large number of very bulky old valve radios, and I'm more interested in the current technology anyway. But when you see articles by noted authorities on the history of, for example, video recorders, and they're good and they're well referenced, lavishly illustrated. Another article I can recommend, this is from July 2020 edition, and thank you very much, John Fleming, for these. That, I suppose you could call the first integrated circuit radio, 3 valves in one envelope, made by the Loewe company in Germany in the mid-1920s. The first instance of circuit elements plus the valves being stuck in an evacuated envelope. An IC, if you will, from the 1920s. Of particular interest to me, and possibly to listeners that have been on here listening on our Saturday nights for some time, are articles that were published by Brian Kirkby, who's a descendant of the Charles Edward Kirkby, who was one of the people in Father Archibald Shaw's Australian Maritime Wireless Company. He's there in the front, pre-First War. This was the organisation that built the Flinders Island spark-based maritime wireless station in 1913, which survives so magnificently on private property on Flinders Island. And in Kirkby's article you can actually see the workshops in Randwick where the various pieces of equipment for that station were made. So, Historical Radio Society journals, a little swag of them there from John Fleming, and sincerely appreciated, John, if you're watching or listening tonight. Very, very good. Tonight, the predominating theme will be audio quality via shortwave radio. Can it be done? What are the techniques? How much success has been had? Well, I'll be covering 2 instances of transmission on shortwave radio, HF radio, tonight. One is the broadcast form, and for the last 20 odd years on HF there have been transmissions of Digital Radio Mondiale, an entirely new approach to shortwave radio using multiple subcarriers, carrying numerical digital information to reconstruct the original speech and music with clever codecs. And I've been really surprised to find that there are a good dozen broadcasters around the world, some of them with multiple transmissions, undertaking Digital Radio Mondiale DRM transmissions on HF radio to this day, with varying quality, very variable quality. Here, for instance, is from 7315 kilohertz, a sample of the end of the French radio transmissions and the start of the English from Radio Romania, from their transmitters at Galbani in Romania. And this is transmitted at 11.64 kilobytes per second. I must say the quality of these, it's odd. Sounds okay, except that there's very synthetic sibilants, S's, T's, frictives, which sounds a little like a detuned AM transmission. It could be a function of the fact that I'm recording these off web-based software-defined receivers, which have a button to allow the reception of DRM, and that extension on the web-SDR program doesn't work terribly well. Maybe not. Maybe it would sound better if it was directly received. But anyway, here is Radio Romania, a sample of their transmission recorded at 6:30 AM Melbourne time. They're on most days of the week on 7315 kilohertz.
De les encourager et de leur donner l'occasion de s'exprimer et bien sûr de les rassurer.
Sur ce prend fin cette émission de Radio Mondiale Internationale. Merci d'avoir été à l'écoute. À bientôt.
Radio Romania International. You are listening to our half-hour broadcast in English for listeners in Western Europe and North America, the East Coast. We can also be heard on the internet at www.rri.ro Channel 1. You can find us on Facebook, Twitter and other social media platforms. Our programs are also available on TuneIn and via satellite Eurosat 16A on 11,512 MHz vertical polarization, azimuth 16 degrees east. Symbol rate 29,950 megasymbols per second, standard DVB-S2, modulation 8 PSK, audio PID 510. We wish you good reception conditions. Welcome everyone to a new broadcast coming to you from Radio Romania International Studios in Bucharest. I'm Vlad Palcu. Let's look at the top stories.
And now an example of the BBC's transmissions of Digital Radio Mondiale. This is the 15620 kilohertz 20-meter transmission of the BBC using 16.92 kilobytes per second transmit rate, and this was recorded between 6 and 7 p.m. Melbourne time, 15620 kilohertz.
This is the BBC World Service, and I'm Gareth Mitchell with a special edition of Digital Planet. The show is 20 years old, so we're looking back on what's happened since that first edition in 2001, the advent of the smartphone and mainstream social networking. But there have been worrying developments too, like data scandals. It's been quite a ride overall, so with team members past and present, we'll bring you a few highlights from over the years. It's all coming up after the news.
BBC News with Neil Nunes. United Nations scientists say the number of weather-related disasters around the globe has increased fivefold over the past 50 years. But far fewer people now die due to storms, floods and droughts, thanks to better early warning systems.
This is the BBC World Service. What are you looking for?
Why was "How long does a bee live" one of the most popular searches in Germany? What was behind the question "How to make him love me again" being asked over and over in Peru? What can we learn about a culture from what they search for online?
The World According to Search at bbcworldservice.com/documentaries. In times of need, we are there with emergency warnings to alert you to keep you safe. Digital Radio Mondiale, much more than just a radio. For information, go to drm.org.
The BBC and Digital Radio Mondiale. Better radio.
Another BBC transmission intended for reception in Europe only, and in fact I decoded this from a web-based SDR in North Wales, is this transmission on 3955 kilohertz, 80 metres, or perhaps I should say 75 metres. It's also 16.92 kilobytes per second bit rate.
Hello and welcome. This is Newsday from the BBC World Service with Lawrence Pollard and Rahul Tandon.
Coming up, as US forces leave Afghanistan after 20 years, what happens next? In this hour, we'll get the thoughts of our South Asia correspondent, and we'll be shortly hearing from someone trying to get 600 students out of the country.
Hurricane Ida has been described as the poster child for a climate change-driven disaster. We ask how to stop similar events from happening.
Isaac will bring us all the latest on Day 7 of the Paralympics, and we'll be hearing from a South African gold medalist at the game.
Also, the fraud trial opens of former billionaire Elizabeth Holmes, who was going to change the face of medicine. It's the remarkable Theranos story, raising all sorts of questions about investment in tech and Silicon Valley. We'll get the latest on that dramatic tale, plus the business with Andrew Wood as well. Security analysts as well. Let's hear from one now. Lieutenant Colonel Daniel Davis, once served in Afghanistan, is now a foreign policy analyst with defence priorities. What's going to be the legacy of this chapter of US foreign policy intervention?
An avoidable failed war that was shrouded in lies. I mean, that's kind of the one answer I would give that captures the futility of what we tried to do and our unwillingness to acknowledge patently obvious ground truth reality that the war was not winnable. Yet instead of coming clean to the American people and to the public in the West at large, we just kept lying about it and telling people, no, actually it's succeeding, we're making progress. And we just kept covering that over with lies year after year until finally the results of those lies were so egregious that the Afghan government and military virtually collapsed overnight across the entire country. And then the lies could no longer be covered, and we were left with the ugly truth of what has been known for a long time.
Pretty good headline from you. Listen, when the president tries to square with the American people, what do you think he's going to say? What do you think he should say? I mean, he isn't going to use the word defeat, for example, but analysts are going to have to, aren't they?
Well, we lost the war. I mean, let's just point blank say it. We lost the war, and there's no two ways about it. It can't be spun any other way. And I don't know what the president's going to say. I mean, what he has so far, he's implied that he recognizes it. And, he says that our original plan to go in there, our original purpose was accomplished, and it was by 2002. And as I've argued many times, that's when we should have ended the military phase and withdrawn our troops and turned it into a humanitarian operation to help them rebuild according to their desires and according to how they wanted to govern themselves. But we couldn't do that. We couldn't take the win. We had to turn it into a nation building and just got greedy and want more and more, and we ended up with nothing.
Interesting. Mission creep. Is there one place to point a finger? I mean, you sound angry, disappointed. You're saying the Americans deluded themselves. But who do you blame? Who do you point the finger at?
Well, I mean, there's a couple of different parts. And, you know, there's no one father to this disaster, and there's no two ways around it. The Afghan government also deserves considerable criticism and responsibility for what happened, because they had 2 decades to get their house in order, 2 decades to build a powerful and at least capable security force to get rid of the corruption to at least historical, you know, cultural norms, which they never came close to doing, because there were too many people that were individuals that were empowered and wanted to keep power at the expense of building an effective state. So that's one. But the second one, and where I put most of the blame, is on our own country, because too many of our leaders knew that. They saw it long ago, and instead of, you know, making some hard deals with the Afghan government and holding them firm and accountable and saying, hey, you either get this done or we're going to withdraw or we're going to withhold this money, something, we did nothing. So we knew the corruption was going on. We turned a blind eye to it, and Karzai was really bad, did lots of bad things, but he has a couple of things he said do have some credibility, that we facilitated a lot of the corruption, and there's certainly some truth to that. But the bottom line is the most important thing, and the reason for the emotion I think you can hear in my voice is that so many people died because so few leaders were willing to do the right, hard thing when they had the chance.
Lieutenant Colonel Daniel Davis helping us write the first draft of history, I think. This is Newsday, back after the news.
This is the BBC World Service. What are you looking for?
Why was "How long does a bee live" one of the most popular searches in Germany? What was behind the question, "How to make him love me again," being asked over and over in Peru? What can we learn about a culture from what they search for online?
The World According to Search at bbcworldservice.com/documentaries.
10, 9, 8, 7, 6, 5, 4, 3.
There are many other DRM transmissions on HF radio if you care to look for them. All of them have that appearance on a waterfall display, such as you get on a software-defined receiver, of being a band of frequencies being transmitted about 9 or 10 kilohertz wide. There are many stations with many different types of programs. There's a station from Pennsylvania called WinB, transmitting a band of DRM only 5 kilohertz wide, and they're kind of a holy roller Christian station, transmitting all the usual televangelist stuff, 8.28 kilobytes per second. Much better audio quality, though, from, of all places, Kuwait radio. Kuwait. On 2 frequencies. This is the 11.965 megahertz transmission, 31 meters, which is transmitted at Melbourne time, 2:45 p.m. to 6 p.m. daily. And this 11.965 kilohertz transmission was demodulated from the VK5ARG web-SDR at Tarlee, about 100 kilometres north of Adelaide.
This is Radio Kuwait. The time now is 8 a.m. Kuwait local time, 5 GMT. This is Radio Kuwait, transmitting on 963 kilohertz on the medium wave for our listeners in the state of Kuwait and the Arabian Gulf area. The local listeners can also receive our transmission on 93.3 megahertz on the FM band. As for our listeners in South and Southeast Asia, we are transmitting on 11970 kHz on 19-meter band on the shortwave.
GCC, Joint Program Production Institution, presents Under the Umbrella of Islam, Part 2. Allahu Akbar. Allahu Akbar.
In the Indian subcontinent, DRM is very prevalent. In fact, I was amazed tuning into a Bangalore-based web-SDR to find that most of the activity on the AM broadcast band was DRM, or at least had analog AM next to the DRM equivalent on the dial. And this is an example of Air Bangalore received on 603 kilohertz with a 7.7 kilobyte per second signal. A particularly good example, actually, in terms of audio quality.
इसी समय सुन सके। ये कार्यक्रम आकाशवाणी के दिल्ली केंद्र पर तैयार किया गया।
अमेरिकी राष्ट्रपति ने कहा कि उनका देश अफगानिस्तान और अन्य देशों में आतंकवाद के खिलाफ लड़ाई जारी रखेगा।
We will maintain the fight against terrorism in Afghanistan and other countries. We just don't need to fight a ground war to do it. We have what's called over-the-horizon capabilities, which means we can strike terrorists and targets without American boots on the ground, or very few if needed. We've shown that capacity just in the last week. We struck ISIS-K remotely, days after they murdered 13 of our service members, dozens of innocent Afghans. And to ISIS-K, we are not done with you yet.
राष्ट्रपति रामनाथ कोविंद 6 सितंबर को गोवा के नौसेना केंद्र हंसा में नौसेना की उड्डयन इकाई को राष्ट्रपति ध्वज प्रदान करेंगे। डाक विभाग इस अवसर पर विशेष डाक कवर जारी करेगा। राष्ट्रपति ध्वज राष्ट्र के लिए की गई असाधारण सेवा के सम्मान के रूप में किसी सैन्य इकाई को दिए जाने वाला सर्वोच्च सम्मान है।
At the other end of the quality spectrum, unfortunately, is this signal that I intercepted from All India Radio on 9620 kilohertz. Something was radically wrong here. I suspect that the people at the station hadn't heard of level controls. It appeared that they have two audio levels at this particular station on 9620, either flat out or zero, and this is flat out.
नमो नमः सर्वेभ्यः। मम नाम गंगा। भवन्तु शृण्वन्तु रेडियो यूनिटी 90 FM एक भारत श्रेष्ठ भारत। अहम् एकता मूर्तयाः मार्गदर्शिका एवं रेडियो यूनिटी माध्यमे आर्जे अस्मि। अद्य संस्कृत दिनम् अस्ति। सर्वेभ्यः बहवः शुभकामनाः अस्ति।
Okay, that gives you a fair idea of the quality, very variable I might add, that can be received by digital means on HF radio. But analog means also have been developing in the last 20 years or so, particularly along the lines of broadband sideband. Now, why broadband sideband? Why isn't everybody quite content to use the existing 2.7 or 3 kilohertz wide sideband audio that we've been used to for the last 50 years? Well, there's a very good reason for that, and it has to do with articulation and listener fatigue, two aspects of ham radio, of any type of radio, including communications quality, where long discursive exchanges go on. Listener fatigue and articulation become particularly critical And let's look at what happens to articulation, the ability to interpret correctly spoken material as you vary frequency response. What I'll do is I'll take an extract, a printed extract from the old Radiotron Designer's Handbook, indicating articulation rates in percentage against frequency response, and I'll wire into the audio stream an 8-stage Butterworth filter at the high and low end specified in the Radiotron. And you can actually see, or rather I should say hear, what happens to the speech signal as we reduce bandwidth. Articulation. The articulation of speech is defined as the percentage of syllables interpreted correctly over any particular communications channel. The results for an average listener receiving syllables at optimum intensity are given as we proceed. First of all, you're listening to a bandwidth of 15 kilohertz with an articulation of about 98%. Now let's reduce to 12 kilohertz. You're now hearing my voice through a low-pass filter at 12 kilohertz, an 8th order Butterworth filter at 12 kilohertz. Shouldn't have changed the articulation much, still 98%. Let's reduce it again. You're now listening to me with a top frequency of 7 kilohertz. The articulation should still be about 98%. Now, the top frequency that you're hearing from me now is 5 kilohertz. 5 kilohertz. And at this point, the articulation has dropped very slightly to 96%, according to tests done over a long period by the Western Electric Company in days gone by. Let's reduce again. The top frequency you're now hearing is 3.9 kilohertz, with only a 94% articulation. This is still much broader than the average single sideband transmission you'll hear today. Let's reduce the bandwidth again. You're now hearing me with a bandwidth of 3.1 kilohertz, or 90% articulation only. 3.1 kilohertz. Let's take it down again. This is transmitted with a bandwidth of 2.3 kilohertz, a top frequency of 2.3 kilohertz, and the articulation is now 80%. As we reduce further, it drops more rapidly. This is transmitted to you with a top frequency of 1.97 kilohertz, 1.97 kilohertz, with an articulation of 70%, 70%. Down further, the top frequency of my voice is now 1.7 kilohertz, 1.7 kilohertz. The articulation level as measured by Western Electric is 60%, only 6 out of 10 syllables being interpreted correctly. Finally, let's take it one final step down. You're now hearing me with a top frequency of 1.5 kilohertz, 1.5 kilohertz, or 50% articulation, 50% articulation. And back to a full frequency response. Okay, now under normal circumstances, a communication channel will limit the frequency response at the low frequency end, the bass end, as well as the high frequency treble end. And under those circumstances, as you vary the frequency response, you can describe as high fidelity, good fidelity, fair fidelity, etc., the sort of communications channel that you've got. Now, I'm about to vary the frequency response according to definitions given in the Radiotron Designer's Handbook with their description of what the fidelity is that you're hearing. First of all, let's limit the frequency range from 62 Hz at the low end to 8K at the high end. I've switched in a filter. This is called high fidelity reproduction according to the Radiotron Designer's Handbook. Articulation 98%. Again, you're listening to 62 Hz to 8 kHz, which will be most of my speech bandwidth. Let's reduce that bandwidth again. This is with a filter of 150 Hz to 7 kHz, defined as good fidelity by the Radiotron Designer's Handbook. Articulation is still at 98%. Reducing it a step further, this is with a frequency range of 200 Hz to 5 kHz, known as fair fidelity or public address standard. The articulation is 96%, still fairly good. We can still achieve reasonably good fidelity if we reduce the frequency response to what I'm about to switch in. And here it is, 500 Hz to 5 kHz. Restricted bass and unbalanced, but you can still understand most of what I say. Articulation 96%. Now let's cut at both ends. 500 Hz at the low end, 4 kHz at the high end, and my articulation should now be 95%, restricted bass and treble. Finally, let's take it another step. This is now you're hearing from 500 Hz to 3 kHz only, very restricted audio, and the articulation should be only 90%. A typical telephone bandwidth of 300 Hz to 3.4 kHz is what you're hearing now. And this is even wider than sideband bandwidth typically. Finally, I'll reduce the bandwidth to a typical sideband channel of 300 Hz to 2.7 kHz. And the articulation is down around 85%. Again, this is a typical sideband transmission bandwidth of 300 Hz to 2.7 kHz, and the articulation is only about 85%. Now back to full bandwidth. So you see, there's a lot missing from the band transmitted typically over HF radio by sideband. And the low frequency end of the speech spectrum gives you a lot of the character of the voice, the individuality of the voice. No need for cutting it at the low frequency if what you really need is to equalize all of the speech frequencies so that they're of an equivalent amplitude right across the speech spectrum. Now, how do we work out what that response is? Well, with modern digital audio editing, there's a graph that you can generate called a waterfall graph. If you're on the YouTube live stream now, you should be seeing exactly this type of waterfall display. The time is displayed on a horizontal axis, the x-axis. Frequency audio frequency is on the vertical y-axis, and the intensity or amplitude of the frequency components of my voice are displayed by the brightness of the various components that you can see waving about on the screen there. Now, the higher frequency components in this are occupied by the consonant sounds, S, T, F, D, all of those. The critical role of consonants in speech presents a serious challenge for any telephone bandwidth network, or any network that uses single sideband 2.7 kilohertz speech channels. The reason for this is that the energy in consonant sounds is carried predominantly in the higher frequencies, which are often beyond the telephone bandwidth cutoff frequency entirely. While most of the average energy in English speech is in the vowels, below 4 kilohertz, which you can see on the lower frequency parts of this graph, that's where most of the amplitude of the voice lies. The most critical elements of speech, the consonants, lie above 3 kilohertz. The difference between F for Freddy and S for Sierra, for example, is found entirely in the frequencies above 3 kilohertz. Indeed, above the 3.3 kilohertz telephone bandwidth cutoff frequency completely. Note how the burst of high-frequency sound that distinguishes S in sailing from the F in failing, watch this, sailing, failing, sailing, failing, and you can see that sailing has far more high-frequency components, but they're all above 3 kilohertz. And the maximum intensity of those sounds are between 4 and 14 kilohertz. When these frequencies are removed, as with telephone transmission or single sideband transmission of a standard type, no cue remains as to what's been said. This makes a conventional telephone incapable of conveying the difference between, for example, my cousin is sailing in college and my cousin is failing in college, without the analysis of additional contextual information, knowing, for example, whether my cousin sails frequently or not. This is with 15 kilohertz of bandwidth. Sailing, failing, sailing, failing. Now with 2.7 kilohertz of bandwidth. Sailing, failing, sailing, failing. Measurements consistently show that the intelligibility of speech decreases with decreasing bandwidth. For single syllables, 3.3 kilohertz bandwidth yields an accuracy of only 75%, as opposed to over 95% with 7 kilohertz bandwidth. This loss of intelligibility is compounded when sounds are combined into sentences. A sentence composed of 10 words, each with 90% reliability, has only a 35% probability of being understood clearly on a telephone channel. In normal speech, words come out at a rate of 120 words per minute. Consequently, 3.3 kilohertz speech produces about 40 ambiguities per minute, whereas 7 kilohertz of speech bandwidth will produce fewer than 4, or close to the accuracy of live open-air speech. We're not conscious of confusion that this frequently causes because the brain has some ability to compensate. When a sound isn't clear, the brain attempts to examine the context of the sound. The first analysis is grammatical. Of the possibilities, which one fit the grammar of the sentence? I have to tie my choose, for example, makes no sense, but The word is probably shoes. I have to tie my shoes. When multiple possibilities fit grammatically, the listener then tries to decide what would make sense in the context of the meeting. Marine biologists may be discussing a dolphin, for example, while French historians are more likely to be pondering a dauphin. However, when presented with a continual string of verbal puzzles as the meeting progresses, the listener is distracted. Pieces of the conversation are lost on these mental detours, trying to deduce what words were used. As this occurs over and over in a meeting or a communication channel lacking high-frequency response, fatigue increases, while comprehension and interaction drop. The listener has to divert his or her attention much more often to figuring out which words were spoken, instead of staying with the flow of the conversation. Too much of the listener's time is spent in unravelling the intended meaning instead of understanding it. And these problems only increase with situations such as lots of background noise, as you find on HF radio, or reverberation in the source microphone environment. And most of that reading came from a publication called The Effective Bandwidth on Speech Intelligibility, published by Jeff Rodman of Polycom back in 2003. A fairly important paper. It's aimed at present improvements in bandwidth, audio bandwidth in the public telecommunications service. 300 Hz to 3K is no longer considered to be adequate for many purposes in public telecommunications, including video conferencing and Skype. Young people particularly find telephonic bandwidth taxing. I think you'll find the average young person finds amateur radio communications quality, so-called, difficult, to say the least, and it would be unlikely to attract them. But as time goes on, it's very likely that we'll have access in amateur radio to better audio quality. And that brings me to the talk by Ivan Vujic VK5RS, which was given at a recent meeting of the Australian Radio and Electronics Group, the same group who operate the excellent VK5ARG web-SDR at Tarlee, north of Adelaide. So here is Ivan. This is republished from the video of his talk with his blessing, I might add. I've had some contact with him the past week. Hello, Ivan, if you're watching. And he will explain the operation of the new ESSB, Extended Bandwidth SSB systems that are gradually finding their way into amateur radio. We may have sideband that's flat eventually from 30 Hz to 6 Kilohertz, and there's certainly enough space on our bands in Australia to accept that sort of bandwidth. Ivan Vujic VK5RS.
So what is ESSB? ESSB is any J3E SSB transmission that exceeds the audio bandwidth of standard traditional 2.9 kHz SSB mode. And you might ask, why 3 kHz plus? I'll get to that in one of my next slides. The main reason for the extended bandwidth is that the bandwidth is directly related to the clarity and required for the clean and articulate vocal audio. And some facts about ESSB. ESSB, a lot of people refer to it as a ESSB hi-fi sound, which is a bit contradicting, considering that the hi-fi term on its own refers to the 20 Hz to 20 kHz bandwidth. But I think that The flat frequency response with extremely low total harmonic distortion and good signal-to-low characteristics is what the ESSB is all about. Amateur radio transmissions, ESSB or AM for that matter, hardly qualify for anything reassembling the true high-fidelity audio. I've heard a lot of abbreviations regarding the E into the ESSB. Some people refer to it as extended, some people refer to it as enhanced or expanded, and I think that the only correct one is extended single sideband. While let me explain this. The normal SSB transmission, let's say the 2.4 kilohertz, can still be enhanced with some external EQing and signal processing, but for the intended purpose it's not extended because it doesn't satisfy the required bandwidth to support the high fidelity audio that's required. Yeah, so we were talking about the benefits of the ESSB in terms of the transmission and reception. ESSB has many benefits, the most noticeable being a very pleasant, highly defined sound, not inherent with traditional SSB audio. Also, it only occupies 1/2 of the bandwidth that required by the AM for the same audio quality, since SSB is a single-side suppressed carrier mode versus the AM, which is the double single-side with carrier mode, and it's therefore a more efficient signal and less subjected to the phasing and selected fading problems inherent with the AM counterpart. The history of ESSB, while experimentation with ESSB has been recorded since the single sideband has been discovered or introduced, the early stages of the ESSB in the modern era date back to the early 90s, and the origins are going back to the America. It should be noted that the single most driving force behind the initial SSB audio experimentation was Bill Salerno, W2ONV, or as he used to refer to himself, one nice voice. Silent key, unfortunately. He was often referred to as the godfather of the SSB audio, and for a good reason. The initial group was catching up daily on 20 meters, obviously doing various testing and testing different modes and different equipment. It's worth noting that back in those days, the transceivers out of the box were not exactly the same as they are today, so some modifications were required in order to satisfy the bandwidth required. Another very important figure in the ESSB scene was John NU9N, who I have contacted to obtain a permission to use some of his website content for this presentation. A very nice guy and very knowledgeable guy in terms of the ESSB audio. And you can find a lot of useful information on his website, which is novemberuniform9november.com. I call this a resistance phase. So obviously that group that was earlier mentioned, that was catching up daily on 14178 in the United States in the early 90s, came up to was facing some resistance from the other band users. There was a lot of people complaining about was it really necessary to transmit 4 kilohertz wide and above for the communication purposes. And there was a couple of petitions being signed in America, I think in 2003, and they were filed with FCC. By those operators in an attempt to ban such experimentation. The attempts failed. The FCC made a decision in all cases, and I think there was 2 of them that were failed officially, one by ARRL and one by one with FCC. both of them were declined, and no changes have been made to the allowed bandwidth in terms of the SSB transmissions. So there was the petitions in 2003 and 2005. Is SSB legal? A lot of people would ask that question, and I think that the reason why people are asking this question, not because they want to be seen as a pain, but because they perhaps didn't know. So this is applicable to the Australian operators. So this is out of Australian LCD, license conditions determinations. So and by definition, any emission mode with a necessary bandwidth not greater than 8 kilohertz is allowed on our bands, referring to VK, of course. So ESSB is no different to somebody trying to transmit AM in the middle of the band, or CW, or whatever that is. CW is not really a wide mode as such, but I'm just taking it as an example. So it's just another segment of the amateur radio hobby. And why 3 kilohertz plus qualifying criteria? Well, high frequency audio above 3 kilohertz supports significant difference in clarity. More suitable frequencies above 3 kilohertz are more suitable for reproduction of natural energy found in a human voice. Most of our consonants of human speech, such as S, T, K, and Z, are all above 3 kilohertz. Human ear is most sensitive at 3.3 K. Intelligibility of the speech decreases with decreasing bandwidth. And in terms of the bandwidth, this is what it looks like in terms of setting it up on your transceiver. So you got the fundamental frequency at the bottom and the end frequency at the top, and the difference between them two is your total bandwidth, of course. And you'll notice that I would say that 2.6 or 2.8 K, that's the reason why I put them up there, would be the most used bandwidths in everyday SSB transmissions, the most commonly used, I would say. So when you do a roll-up on a band with 4.5 K bandwidth, or God forbid 6 K, people will be asking you questions. What are you doing? How do you monitor and how do you prepare your audio to suit desired TX bandwidth? Well, it's important to mention that most radio monitoring circuits are not good enough to give you a true representation of your audio. The way that I found works the best for me is if I just get the signal straight off of my radio antenna port into let's say an SDR receiver, and then record it and play with it afterwards. So in terms of monitoring and preparing my audio and checking the quality of the mix, what I do is you'll see that on a picture there, a little box. I think some people refer to as a sampling port or a sniffer port or something like that. So that one actually provides minus 55 dB of attenuation. So antenna goes into one of the SO239s, and the other SO239 goes into the dummy load, and then I take the little SMA into the SDR receiver to monitor the transmission. On the SDR end, I've got another 35 dB attenuator. So, and I found that to be the most accurate in terms of getting the true representation of what you will sound on air. And then I import that into my audio DAW, digital audio workstation. There's many of them that you could potentially be using. If you remember the previous graph that I mentioned about the bandwidth and the starting and ending frequency, so that's what you can measure on that graph that you, out of the EQ that you have sampled out of your antenna port. And that was indeed one of my audio setups, or one of my audio presets, should I call them. So you can see all the peaks and troughs and the total bandwidth, and where do you cut, and how aggressively do you cut it. In terms of the ESSB setup, and it all starts with a microphone, of course. And a disclaimer there at the bottom, as you can see, credit card warning. So you've been warned. This can get very expensive. So I've seen people with very expensive gear having an average audio quality, and on the other side of the spectrum, I've seen people with a very like the bottom end in terms of the price gear, but set up properly with the amazing audio. So there's not really hard and fast rules in terms of what you're going to achieve with the equipment that you buy. Most definitely, I would say that Neumann microphone is definitely better than the $100 PreSonus one that you see on the left there. In all aspects, dynamic range, frequency response, the polar pattern, you know, whatever you want to compare them, they're definitely going to be chalk and cheese. But again, horses for courses, and be warned, these toys are very expensive. Just as a reference, some of the very popular ones out there amongst the ESSB community would probably be the Electro Voice RE20, the one on the far right hand side. That microphone has been an industry standard in the broadcasting industry, not particularly related to amateur radio alone, but the actual radio broadcast for decades. That microphone was first introduced in 1962 and it's still selling today, so it's not a discontinued model. The Shure SM7B in the middle, and for the reference, that Electro Voice that I mentioned there before is around about 800 to 900 Australian dollars. The Shure SM7B, same price range, I would say mid-range microphone, and then you go on the far left, PreSonus PD70, very recently released. So it's a newcomer to the market, but with some very spectacular results, and a lot of people are praising that product. We're not going to talk about the two middle ones, the Neumann and the Neumann, because they cost over 5,000 Australian dollars, and I think that they would be an overkill for the ESSB. They'll be more suitable for the recording industry and the studio applications. Radio. Okay, so a lot of you would remember this rig. What is it called? Something SDX. This was the ultimate choice back in the 90s, and this radio was, well, first it was capable of doing some DSP, digital signal processing, and second of all, it was doing 4K out of the box, so referring to 4 kilohertz wide transmission without any modification. Needless to say, ESSB people didn't settle for the 4K, so a lot of them have done some mods to extend it to 6+K. And a very popular group for that era was the Voodoo Labs, so the Voodoo Audio Labs group. That was coming up with a lot of modifications for the rigs of that era. So definitely you would have seen or heard a few of them in the mid to late 90s on air. So I would say every single audio lover in terms of the SSB would have had one of them. ESSB rigs of the modern era, in terms of the conventional radios, ICOM unfortunately does not support, and look, I could be wrong, but most of the ICOMs that I've played with, the best I could have got out of them was 2.9 kilohertz in terms of the TX bandwidth. I could expand that by brute force to probably about 3.1 max. And when I say brute force, referring to the external processing and really pumping up some hard audio into it. But that would be the absolute maximum that I've seen on 7300, for example, 7610. So I haven't had a pleasure of playing with the more expensive ICOMs from their range. Yaesu, on the other side, has been very popular lately, I would say within the last 10-15 years within the ESSB community due to the wide TX ability out of the box. And a lot of people are referring to the color of the sound they're getting out of the Yaesus, that warm tube sound. I'm specifically referring here to the FT5000. That's 4K out of the box, FTDX 101, both Delta and Mike Papa, 4K out of the box. And of course, Kenwoods traditionally support the wide TX bandwidth, and it still remains popular within the ESSB circles. And that was my brief overview of the conventional rigs. In terms of the software-defined radios, some major changes are noticed in the ESSB community since the introduction of the modern SDR transceivers. Most of them would do 10 kilohertz bandwidth out of the box, no modifications whatsoever. And I've experienced this myself with NN and the Expert Electronics, and also on a few friends of mine that have flex radios. So really popular and growing in popularity in terms of the ESSB use. And a lot of, but they are, on the other hand, chalk and cheese compared to the conventional radios. Very different to set up, very different to operate. But a lot of these modern SDRs, you probably wouldn't need to put so much effort into external processing in order to achieve the desired audio quality, because a lot of them have built-in voice processors that are quite good. All right, now we're getting to some frequencies and how we explain them. So you'll hear a lot of people talking about frequencies of the human voice, and this is just a very brief explanation of the most popular ones and what do they mean and what can you do with the certain ranges. So 75 Hertz to 200 Hertz is your heaviness and your rumble. I'm not going to use the B word. So 200 to 300 Hertz is your bass and the sense of bigness. 400 to 600 Hertz is chesty boxy sound. 600 to 1K is volume, and then the most important one for me is 2000 to 4000 Hertz, or 2 to 4K, which is the clarity. 3 to 5K is presence, and 10K is the airy sound. A lot of people, and look, I'm one of them as well. I'm very new to the ESSB. I've been playing with ESSB for probably last year, and I have I've definitely experienced the full circle. I've started with one component in my rack. At my best, I had about 8 different components processing the audio before it was fed to the radio, and there's a lot of things to learn, and by no stretch of imagination have I learned all of it. So a lot of people are asking the question, should I cut or should I boost, in terms of obviously referring to these frequencies over there. EQing the signal is one of the most important parts of any audio setup, and the same thing applies for the extended ESSB. You will notice that if you search the forums or ask people that are knowledgeable about audio engineering, that a lot of them prefer cuts versus boosts. Boosting, the most simplest way that I can explain this, for example, a muddy sound can be cleared up by boosting the high frequencies, but that is not a solution that's going to fix your problem. That's just a patch. So boosting the highs, yeah, will cover up the muddy mids, but it's not going to fix up your problem. So you will notice, and that's something that I've definitely learned from my experience so far, that cutting is definitely much more efficient in terms of the voice clarity opposed to boosting. And I'm not sure why we all kind of tend to boost more than cut. That's just a human nature, I would say. But so far, I've managed to convert my mind to say, well, okay, what can I cut instead of what can I boost? And the results are amazing. And where to start for the interesting ones, the people that are interested in doing some ESSB experimentation. Well, I think I mentioned this a few times before. The picture you see here is one of my rack setups, and we got the 1, 2, 3, 4, 5, 6, 7 components, or 6 really. The last one is the sound card. There are no hard and fast rules. The very simple, the simplest form of processing the audio and feeding it into the radio would probably be a channel strip. Channel strip, you can see that the very first component up there, and that's something that's it's a bit of a legendary component in radio broadcasting industry. It's called Symmetrics, and that model is 528. There's also a 628. They're no longer manufactured, and they're hard to find, but if you can find one, grab it. They're worth every single dollar. They're not very expensive, by the way. And why they call channel strip? They call channel strip because they give you the entire channel setup in one component. So that particular component has microphone preamp, it has downward expander, has compressor, and it's got EQ. So that's, for somebody that's interested in starting up with ESSB, will probably be more than enough in terms of processing audio to feed into a radio and get a very decent sound. And this does not apply solely to ESSB. You know, if there are people who are not interested in wire transmission, you can be still doing your 2.4, 2.6, 2.8, you know, whatever. But you know, obviously, if you wanna sound a bit better, that's the way to do it. And in terms of feeding the audio to the to your radio, so far the experience tells me that the front end of the radio should be avoided at all costs, because there's some circuitry that needs to be bypassed, and you can do that by feeding the audio from the back, which has resulted in much cleaner sound and a better dynamic range. And of course, I need to mention that I do have a particular friend who runs a software setup, so he doesn't have the knobs and dials. He has got his entire ESSB setup done on a computer, which you can do again very easily nowadays with the DAWs and all the available plugins that are easily accessible on the internet. Some of them cost a lot of money, but you can do a good job with the free ones as well if you know what you're looking for. Okay, so I think that I'm not going to dwell too much on the setup tips, but from the experience, the most important things that I've found are the microphone is obviously the number one thing. This is where you start. Microphone should be connected using a balanced connection, balanced cable, and don't try to cut corners on cables. This is very important. Good shielded cable is not cheap, but it's worth the investment. Also, for the people that are interested in processing audio and feeding it into the radio, I need to mention, I put in brackets there, don't forget audio transformer. I need to mention the fact that the all Pro Studio gear, referring to the rack components, by default plus 4 dBu on the output in terms of the output level. What we need for the radio input is about minus 40 dB. So there's a bit of a difference there. So if you are to plug the output of the symmetrics that you've seen on the previous slide directly to the radio, it's not going to be a good thing. You could be damaging something, or definitely not going to be sounding very well. So that needs to be attenuated a lot. And there are various suppliers out there that provide the audio transformers. Noise reduction is the other thing that I've noticed, because the mics are normally very hot because of all the external processing, and you'll be amazed with what sort of noises they'll pick up. So and also the shacks can sometimes be a very noisy environment where you got the amplifiers running, you got the fans, and all sorts of noisy equipment. Hum is normally, so before I go on to the next thing, so the noise can be dealt with either the noise gate or the downward expander. One of them two will, you can set it up so that you'll cut off all the noise at certain level, so the background noise is all eliminated and your voice can still be processed without interruption. Hum in audio transmission is normally introduced by ground loops or bad cabling, and the hum is and it could be prohibited by correct connection between the different sound process equipment. This is what I was referring to before with the quality cables as well as the filtering. We already spoke about the AGC. Well, we didn't speak about AGC. We spoke about EQ and AGC. We all know what AGC is, auto gain control. I don't need to spend a lot of time explaining that. AGC is designed to change the input gain in a way that overall signal level of the recorded voice is nearly constant. So it rides the gain, is the typical term you're going to hear. The AGC can reduce or increase the signal level. Compression on the other side, which is not on the slide there, is doing completely opposite. So you need to be careful that you're not pushing those conflicting operations too much in opposite ends, as you're going to run into problems. In terms of the signal process flow, and again, there's no hard and fast rules about this, but this is what I would say a very average voice processing rack would consist of. So of course you got a microphone, then you're going to feed the mic into your microphone preamp. Out of the microphone preamp, you got to obviously put some sort of gate or limiter in there to deal with those noises we mentioned earlier. Out of that, you're going to EQ your voice, compress it, and put a bit of color onto it with some effects such as reverb, and then feed it into the radio. This is a very debatable subject. A lot of people would ask, do you compress before? Do you compress first and then EQ, or do you EQ first and then compress? So I personally, I like to have my gate or limiter straight after the microphone preamp, because that means that all the unwanted noises are eliminated right at the front, and I like to do my EQ straight after that. The reason why I like to do the EQ is because the compression can affect the EQ, especially if you're running a broadband compressor. And I'm not going to get too deep into the compression, but there's various compressors out there, and there are some compressors that will do multi-bands. So you can set up different parameters for the lows, mids, and highs, and how they compress each segment individually. Or you can have just a cheaper compressor that just compresses the entire spectrum at once, And why is that a problem is that, if you, especially in ESSB setups, a lot of ESSB people like the bottom end. So you'll notice a lot of heavy bottom end in terms of the bass. And when that bottom end hits the compressor, that's what triggers the compression to start its process, which means that sometimes the high end escapes the process unprocessed, if that makes sense. And I obviously mentioned the on the output. Before I got to the output, the reverb. Reverb is one of those effects that I don't think I'll be able to imagine my setup without one now, because I'm so used to it. But without it, it sounds like you're talking to a pillow. It's very muffled sound, and the reverb gives it that increased presence and a bit of a airiness in your transmission. But you got to be careful with reverb. You don't want to sound like 1980 CB operators. And no disrespect to the CBs, but it's just too much reverb will sound horrible. So it needs to be the right amount of the reverb. And again, I've already mentioned the audio transformer on the end of the output from the rack going into the radio, which is very important considering the difference between the output and the input required for the radio. Alright, so the limitations of ESSB. First limitation of ESSB is for, and again referring to Australian users, would be the power. As we all know, in Australia we are limited to 400 watts PEP. USA users, for example, can have access to 1.5 kilowatts. Majority of the population that would listen to your transmission would either not know what you're on about, or you will sound very horrible to them because they're receiving a 2.4K, and their receiver is not really not really presenting your hard work in terms of the audio they're going to hear on the other end. Receive quality is mainly dependent on a signal strength. In order to hear the high fidelity sound, you would need to be receiving my signal, let's say, for at least 5 dB over 9. If we're talking, 5.7, 5.8, yeah, maybe. But yeah, 5.9 plus 5, 5.9 plus 10, ideal. Because there'll be no noise, the audio transmission will be crystal clear, and you'll be able to hear everything that's been transmitted in terms of the audio fidelity. DXs, forget about it. Definitely not your thing. If you are intending to burst pileups, it's definitely not a thing not intended for the DX operation, I would say. A lot of people will argue this point and say that it can be used for DX, and no doubt it can be used, but I'm just thinking that a lot of energy has been in DX application, let's say, it's been on ESSB signals has been wasted on the high and the bottom end, and you're not going to be heard very well. And in a pile-up situation, you're definitely not going to have a chance. And I've tried it before myself, and the difference that I've got in terms of the amount of people I can work on 2.8 versus 4.5 is just amazing. So yeah, with new solar cycle on an incline, maybe that's going to change things. I haven't seen the good old times or the last solar cycle, so I can't really comment on that. 95% of the ham population, regardless of where you are in Australia or not, will be TXing or transmitting and receiving on, I would say, approximately 2.6 kilohertz wide, and receiving in the same fashion. And again, they won't be able to hear your high fidelity sound. And be prepared to be told that you sound like woof woof, and to be criticized for your TX bandwidth. You know, I've received a number of messages and warnings and on air, off air, saying that, you know, I'm not going to make a lot of friends transmitting 4 kilohertz wide. But again, you just need to be mindful of people around you, and make sure that you play wide ESSB when the conditions permit. Okay, so why ESSB? It's a personal choice, and please remember that audio is extremely subjective. It's almost like I like red, you like blue. It's just another mode, so it's same as CW, FT8, RTTY, EME, etc. And whatever you do, please remember to acknowledge others. Like I said before, if there is a contents on and you see, you know, hundreds of signals around you, don't try playing YTX, because you're not going to be liked a lot, and obviously do that when the conditions permit, when the band is empty. Do it perhaps on the band edges where you're not interrupting with anybody else, and you're not splattering onto people nearby. But at the end of the day, I think ESSB is about experimentation, which is the core of amateur radio hobby, and you should remember to have fun and never stop experimenting. In terms of the ESSB, I think it's important to mention also that apart from the high fidelity of the processed audio, it's important to mention that ESSB operators are very persistent and very adamant on transmitting a very clean signal. When I say clean signal, I refer to IMD free, well, minimal IMD in the TX audio. And experimentation with ESSB will definitely make you a better operator, because you'll be facing a number of challenges, and some of them would be RFI suppression. So obviously STRI-RF coming back into the shack and getting into your audio, cabling, grounding techniques, and of course in-depth equipment adjustment, as well as many other factors that lead to a high quality signal. This will definitely expand your knowledge and harness skills otherwise not realized with simple plug-and-play SSB operations practiced by most. Alright, so I think that is the end of my presentation. Again, I would like to thank you for your time and attention. And oh yes, that's right. Thank you, Grant. No, that's it. All right. So just a bit of instruction. We are going to play about a minute and a half of the ESSB audio transmission recorded live off air. Just 2 stations from USA. And if you are really willing to hear the high fidelity that these people are broadcasting, put your headphones on, because if you listen to this on your phone or out of the computer speakers or something like that, you're not going to be able to hear the true representation of the audio quality. So here we go, the sample of the true extended SSB, and that was recorded at 4.5 kilohertz.
Just think about, oh man, 40 meters or even 10 meters. I mean, a 30 or a 40 over signal on that band, absolutely quiet.
It's gonna be illegal.
As a fact.
You know, Paul's gonna be, he's gonna hear this and go insane.
Oh yeah. Well, I'm recording it right now, so I'm just trying to get my level set. And it's a little screwy at first, but we got it going on.
That's right. He's gonna nut up and have a cow, so that'll be good. We'll have to send that to him, email, and tell him, say, look, man, here's the nuts in the bag right here, and you need to get off your rear end and get your butt back on the air so we can play some audio.
That's it.
Oh yeah. Well, I'm recording it right.
All right, and that concludes our presentation for tonight. Thank you once again, and I'm pretty sure Grant will ask if there's any questions.